All right, I'm back. I'm on the, I don't know, I'm kind of in the middle of 245, I guess. We are going to use the general equation of a semicircle to come up with a formula for the volume of a sphere. This, in my opinion, is one of the coolest things that we've done all year. It feels like very high level. It gives you a lot of insight into like where do formulas come from. The interesting thing is it's not the original place that the formula came from, and that's like crazy. I think I mentioned Archimedes before. He had like stacking like spheres and cones and taking away stuff. Like that guy was a genius. Uh, we get to stand on his shoulders, thankfully. Actually, we're kind of really standing on Isaac Newton and Gottfried Leibniz's shoulders right now. They're the two guys that at the same time basically developed calculus, different notations, same ideas. Newton gets all the credit for some reason. Anyway, let's do this, right? So I'm going to start with a picture. It's basically the same problem over again that we just did. So we're here, and so this is negative r, and this is r. So my delta x, everything's going to look a little weird, is going to be r minus negative r over n. So it's going to be 2r, the diameter, over n. X sub I is going to be where we start, which is negative r, plus I times delta x, so 2 times r times I. I'm going to write 2r over n. I put the I in front, so I times 2r over n. Okay, my volume formula is going to be the sum from I equals 1. I feel like I got really lucky when I was drawing that. My pen felt all out of control, but it came out sort of okay. N of pi, the radius, so the radius comes from this, so f of x sub I, it's always f of x sub I squared, and then delta x. Okay, and then the calculator is going to do the work for us because we honestly have no idea how to do this yet. But you could actually, some years when we have time in class, I do it by hand because it's amazing. And you just have to like remember a couple of those formulas that we went over in the last video, like the sum of I squared. But now feels like maybe it's not the time. So I'm not going to do that. The limit as n approaches infinity of v of n will be equal to something. Let's have the calculator find it. I mean, we know what it's going to be equal to, but like the cool part is like seeing it happen. So here's our calculator. Maybe a new problem. And then add a calculator page, f of x, going to be equal to square root of r squared minus x squared. So semicircle, a generic semicircle. Volume as a function of n, v of n, going to be equal to. I'm going to put the pi on the outside. I'm going to vary it up. I'm going to put the, I'm going to risk it and put delta x on the inside. So the sum from 1 to n. You can put the pi inside too. It's like, it really doesn't matter. If it doesn't depend on I, it can go anywhere. It can go inside, outside. You can factor it out. That's how you get it out. You factor it back in. It has to do with the distributive property, which I'm sure you're familiar with. So I keep looking off to this side because my other computer keeps going to sleep for some reason. It's not supposed to. And it's really letting me down. All right, so the radius f of negative r plus 2r over n times I got to square that. Then I got to put in delta x. So I'm risking it. Ooh, putting it on. What has happened? Ugh, abandoned ship. I'm just going to put it on the outside. It looks like everything is defined. Why are they all bold? I am a little concerned about that. But let me finish anyway. So this is 2r over n. Ugh. Okay, it went back to normal again. I don't know what happened there. That's basically what I do though. When things aren't going how I want them to, I like just stop and try something different. Or sometimes I'll actually outright delete it because it's just like, it's not worth the risk. And there's like, there's kind of nothing you can do about it. Sometimes that happens. N goes to infinity. What happens to me a lot when I'm using solve is somehow like, if I'm not using the system, I'm doing like menu 3-1, be like solve this equation and this equation. If you can picture that. In the second equation, if it starts with a fraction, when I try to do the fraction, it puts and in the numerator of the fraction. And it's like, you can't fix that from what I can tell. And that's terrible. So, you know, just things. I know that that happens and I do it all the time. Okay, this is the moment of truth. Will I get 4/3 pi r cubed? Ah, 4/3 pi r cubed. Isn't that amazing? So, like, we already knew that, but that's it. That's really cool. That's like worth showing someone. I don't know who's in your house, but maybe try to show them. See if they were interested in this. All right, let's go back to the notes. Hopefully they're interested in this. I mean, you know, you're interested in it, so make it come alive for them. Just talk it up. 4/3 pi r cubed. You got to be an ambassador for this stuff, you know? You're not just here for the education. You're here to spread the word. All right, the next question seems super open-ended. Find the volume formula of a cone with radius r and height h. Okay, so what I'm going to do is draw a picture and just work this out. So it's got to have a radius of r and a height of h. This might feel very familiar to you if you did the sort of optional problems with rotating things at the end of the last set of notes. It's like basically the same idea. So I want r to be the radius. I'm going to go around the x-axis. I want r to be the radius. So I'm going to say that this is r, right? That's the biggest radius. And we're doing slices, so like the radius will decrease. And then this will be h. This problem is rough because my h's and n's look very similar. It's like with vectors, like u and v. It's like, pick something different, but we didn't. To draw this. And then let's erase this little mark if we can. Okay, look at that. All right, so I'm going to need the equation of this line. So this line is y equals, or I guess I could call it f of x. Let's call it f of x. F of x equals, the y-intercept is r, and then the slope is you go down r and over h, so minus r over h, and then times x. That's like r, h, and n. This is the worst case scenario. They're all here just waiting for us to like make some small mistake, and then we're not going to get it. All right, I need a delta x, which is going to be how far do I go along the x-axis? I go from 0 to h, so it's going to be h over n. H over n. And then I need an x sub I. But we start at 0 and just go, so it's going to be 0 plus. This is kind of fun. We could write high if we wanted to. hi over n. I feel like that's not great, so I'm going to put it in parentheses. H over n times I. And then we want to write our formula. So the volume as a function of n will be the sum from I equals 1 to n of pi. Ooh, bad pi. Look at that. Let's try that again. Pi. Okay, better maybe. The radius, so I'm going to take f of x sub I and then square it. So it's f of I times h over n. I keep going back and forth on how to write that. That's the radius. I need to square it, and then I need to multiply by delta x, which is h over n. Okay, and then what I want to do is I'm going to find the limit of this. The limit as n approaches infinity. So that's using an infinite number of slices instead of using like 50 or 1,000, use infinity. It's one of the craziest concepts in math, but it's amazing like how it just works out. So here we know what we're going to get, I think, but we're going to go to the calculator and make it happen. This is going to be another thing that I'm probably going to tell you to try to find somebody and explain it to them. And I hope you try. I mean, you got to like show that you're interested. People will be more interested if you are more interested. So get out there, share it with everybody. All right, f of x going to be r minus down r over h times x. All right, volume is a function of n. Pi times, got to do a summation. Okay, from 1 to n. You might be wondering about that big pi symbol that's right next to the capital sigma that is the summation. That's like multiplication. Try it out. So try like I goes from 1 to n of I and see what you get. right? And let n be 1, let it be 2, let it be 3. I think it's going to be a pattern that you recognize. And that's like pretty interesting. So see how that goes. Ooh, don't do pi again. What are you doing? F of I times h over n. Then we got to square it. Then we got to multiply by h over n. Okay. And now we want to take the limit. So template, limit, n goes to infinity, cursor right in the way, tab, v of n. Okay, so I think I should get 1/3 pi r squared h. H pi r squared over 3, 1/3 pi r squared h. Isn't that amazing? I love that. Like, you can work out these formulas now. You don't just have to be like, where does that come from? You can offer people a place that it comes from. Maybe not the original place it comes from, but a place. So I'm going to go back to the notes, and I'm going to fill that in. And then I'm going to stop this video. And obviously, because there are more pages, I will be back to fill those in. So we got 1/3 pi r squared h, which is exactly the formula that we know for the volume of a cone. So that is very cool. All right. I hope you are finding this interesting, because this is like really interesting stuff. I'll be back to do more with you. See you then.